Okay, so I'm Han from eBay. Today my topic is OVN controller incremental processing. First of all, let's look at the distributed, the OVN control plane, which is the distributed control plane. There are central part and distributed part. And OVN controller is distributed on all the hypervisors and gateway nodes. It's watching the sourcebound DB and translate and process the changes from sourcebound DB on every hypervisor and gateway nodes to translate logic flows to open flow rules and install to OVS. So there's some challenge of the scaling of this component. Basically, the size of data to be processed by each OVN controller matters here. Because of a distributed logic router implementation, it requires that every hypervisor needs to process the data for all related logic port and data parses so that the traffic can be directly forwarded from one hypervisor to the destination hypervisor. So it's like a full mesh kind of connection. And for example, 10K logic ports requires at least 40K logic flows and 10K port bindings. That's a decent amount of data to be processed. Secondly, the logic flow parsing is actually very CPU intensive. And thirdly, the cloud workload changes frequently, like the VM boot container up and down. So this is a pretty much dynamic control plane. And current implementation of the OVN controller is like always recompute everything whenever anything changes in the input. And even if there's no change at all, but just some events that triggers the main loop, it will do all the calculation from beginning to end. So it takes a long time. And the benefit of this approach, of course, is obvious. It's easy to implement and maintain, but there are problems. So basically, the first problem is that it's a big waste of CPU resource. The waste is on every hypervisor. So just like some talks I mentioned yesterday, there's a big tax to pay. And secondly, this is a high control plane latency caused by this recomputing. So assume there's a change happened in the control plane, a VM is up, but it takes some time, actually seconds or tens of seconds, depends on your scale, so that the VM can actually talk to the, communicate with the rest of the work nodes. So to solve this problem, we introduced the incremental processing. Before going to the implementation, the logic, but we firstly introduced the incremental processing engine, a framework that is generic so that we can capture the model and handle the problem in a structured way so that we can, that can help the maintenance of the code instead of introduce a lot of unreasonable complexity, because there's too many inputs to be considered when calculating the flow. So the idea here is a DAG directional acyclic graph that is representing the dependency. For each node in this graph, it's either input node or output node or intermediate result node, which is both input and output. So each node contains, maintains its own data and has links to the input nodes and has a change handler implemented for each of its input, but this is optional. We don't have to implement all the change handlers for every input. So, but it has to implement a full compute handler, which is like currently how it's implemented in the current upstream code for the calculate output. And the logic of the engine execution is pretty straightforward. It's just traversing the graph from the final output. And when there's a change in the input, it invokes the change handler for that input. And if the input change handler is not implemented, or if it's implemented but it's too difficult to handle for that particular change, it will fall back, the engine will fall back to call the recompute handler, that is, fall back to the recomputing. So this is not an on-off approach. It is provide the flexibility so that we can implement this incremental processing gradually we can focus on the most frequent changes inputs, make sure we can get the improvement for performance with minimum effort. So this is a real dependency graph of the current implementation of incremental processing in my branch. This is, you can see there are many inputs, and the green boxes are the southbound table, and the blue boxes are NOC OVSDB table. And there's some other nodes. Of course, the final output is a flow output node. The boxes with orange line are the ones we have implemented the change handler, which means they can be processed incrementally. So they are implemented because they're most frequent changes, just like VM container up and down, it will trigger southbound port banding change, multicast group change, the data flow, the logic flow change, etc. And the one MAC banding is particularly useful for eBase use case because we're running containers in the VMs. So we have mixed workloads, some of them are VMs, some of the containers, but containers are not aware, it's not in the OVN's control. So we are relying on the dynamic ARP resolving to forward traffic to the container that's running in the VMs. So the MAC banding processing incrementally is essential to this scalability of this kind of workload. So another particular interesting case is the port banding. So you may notice that port banding has its input for both runtime data node and flow output node. Both of them have implemented the incremental, the change handler. However, there's no link. The link between runtime data and flow output, the change handler is not implemented yet. So that means if the southbound port banding change causes any change in the runtime data, actually runtime data will fall back to full recompute, and the port banding will not be processed incrementally. It will still use a full recompute. That particular case is actually, in reality, when a VM is boot up, it will land on some hypervisor, and port banding happens there. So on that hypervisor, on that particular hypervisor, where the VM is landed on, the OVN controller will fall back to recompute. But for every other hypervisor, they will just process that change incrementally without too many CPU costs. So the problem of this approach, firstly, is how to make sure the dependency graph is correct. So actually, there's a lot of effort paid. So firstly, thanks, Ben, for providing idea of functional programming. So the idea is to make sure each engine node, the output depends only on the input, so that we can make sure there's no unexpected dependency in this processing. And for that to happen, we removed the global OVSDB IDO handle from the engine node. We actually changed the, also it's come from Ben's patch, that changed the OVSDB IDO implementation to provide the interface that you can directly specify a table instead of a whole DB handle to a function. And then we removed the global variables from the engine accessing node, engine functions. And then another issue is about special interesting feature of OVSDB IDOC implementation. So when there's a table references another table, IDO provides you the convenience that you can access the data structure directly to access another table's data. But this creates a problem for the dependency discovery. So the approach is we actually fix change the IDO change tracking implementation so that in this example, output A node depends on table 1, and table 1 reference table 2. So when table 2's record changes, the change tracker will discover that and create a record in the change tracker so that it appears like table 1 has changed. So output A node will be triggered to to process the change for table 1. So this way we can properly discover the dependencies and make sure it's correct. And the second challenge is the change handler implementation itself. So this is, I think, is the most complex part, and it's pretty like joins between the data flows, because each input you can think about is the data flow or database table. The direct approach maybe you can think about is like some kind of symmetric hash joins, but when there are too many inputs, it's very hard to implement. So the pattern here is we're trying to reuse the existing functions as much as possible, so that functions like such as consider logic flow, it's very handy, but entry point is always a logic flow. So the pattern is we build hash indexes between the other input and this logic flow input, so that this example demonstrates that when a logic flow changes, we use the hash index to find the corresponding final output open flow rules and delete old flows and call this function consider logic flow again to recalculate the desired flows. But if a logic flow is using some address set, if the address set is updated, then we use another index that maps the address set to the logic flow table entries, and we can find out again from logic flow table according to the logic flow to open flow index to finally figure out the chain and figure out what should be updated. So let's look at the result. The first thing is the CPU efficiency improvement. We run the test in the scalability testing simulation environment. So we used 20 bare metals to simulate 1,000 hypervisors, each one with 40 cores. To run this test, originally it took around 6 or 8 hours, I forgot, but from picture you can see that it's with the incremental processing branch, the total time has reduced more than half. And that's because originally without incremental processing, all the CPUs, all the OVN controller processors are very busy, like 100% CPU utilization on the bare metal. So each bare metal has 50 OVN controller in this simulation environment. Each bare metal has 50 virtualized hypervisors running there. And they are kind of competing in the CPU core. So the whole bare metal is 100% CPU usage. So that slows down the whole processing. But with incremental processing, the CPU efficiency is improved a lot. So it's finished much faster. And if you look at this CPU time graph, it's much more obvious that almost 90% reduced the total CPU time. And another test is about latency improvement. So on top of this 10K work node created in the scale environment, we created one more port and see how long it takes for end-to-end control plane process to finish. That end-to-end control plane change actually takes a lot of steps. Like firstly, you have to Nosty will calculate the flows for the new port, and then the southbound DB will be changed, and then all the hypervisors will notice that change and do the processing. And the one actually with the port bandit will do much more processing because, as mentioned before, the recomputing is not, the incremental processing is not there yet when the port banding happens on local chassis, local hypervisor. So from this graph, you can see still not a big improvement in the end-to-end latency, but I want to emphasize that this is a test result in the simulation environment because the bare metal that is running, each bare metal is running with 50 OVN controllers. So without incremental processing, they are kind of competing CPUs, but in the real deployment, this will not be that big difference because you will get enough CPUs likely in a real environment for every hypervisor you maybe, if you dedicate one core for the OVN controller, of course, you will be much faster than this simulation environment testing. But still, there's some improvement even in that case because there are several steps in the end-to-end processing. And some steps is you have the incremental processing even in the local chassis. Some steps you have to do recomputing. But the point here is with the incremental processing, only the local chassis, the chassis that has the port banding created will do the recomputing, and all the other hypervisors will do incremental processing. That will not cost any significant CPU. That's the major point of this testing. Okay, so let's talk about the further improvement of this approach. The first thing is, as we can see, we can do some more incremental processing, more change handlers, so that the particular case is, like I just mentioned, when the port banding happens on the local hypervisor, we can split the runtime data node to some more node and implement more change handlers so that it can further improve the end-to-end latency. So that even if the port banding happens on the local chassis, we can make sure it's incrementally processed. So end-to-end control plane latency can be significantly improved. Another thing is incrementally flow installation. So with the incremental processing implemented, current bottleneck actually in OVN controller it becomes OFCTL put function, which is doing a full scan for between the desired flows and installed flows and figure out the difference and then send to OVS to enforce the change. That is actually not necessary. So I think it's kind of low-hanging fruit to further improve. So that when you get a bigger scale, you can still run with relatively low CPU cost. So is that the end of story? No, because we think, so basically this change hasn't been upstream. Actually, it involves a lot of effort from many folks from community like Mark, from Red Hat, and some other folks even contribute some performance testing. And Ben also, he spent a lot of effort to refactor code so that input and output to be more clear as a functional way. So, but the reason why it's not upstream is because we still want to have a better implementation because the change handler itself is still a little bit complex. Although we have the engine framework, you can define dependencies clearly, but to implement change handler is still a little bit pain in C code. So do we have a better way? The answer is yes. So at least we think it's very promising. And thanks for Leonid from the VMware research. He provided another solution called differential data log or DD log. He open sourced it, which is based on another open source project called differential data flow. Basically, it's a data flow approach, but he implemented this data log language. So it can incrementally processing data flows. And we think it's very natural to be used in OVN processing because OVN, as you can see from the previous slide, the dependency graph is just like data flow joins. And with this language, you can define inputs as relations and then also output as relations, and then you can define rules so that you can generate outputs from inputs. It's pretty declarative, and the benefit is obvious. So because you get the built-in incremental processing, you don't have to write incremental processing change handler manually, and of course it will be much easier to maintain and to add new features. And also, the effort can be reused by both NorthD and OVN controller. Actually, NorthD is making progress by some folks that is already utilizing the we're trying to utilizing the DD-log. So OVN controller obviously will share another outcome from that effort. So what's next to do with DD-log? So firstly, OVSDB wrappers has to be implemented for the DD-log input and output so that DD-log can consume and output the data. And secondly, we need to rewrite the computing logic using DD-log, all the flow parsing related logic. And of course, regression tests and scalability tests. So one proposal from Ben is that maybe we can run two versions in parallel for some intermediate period. And here's an example I worked together with Neonit so that to represent a logic flow to address that mapping, which is a little bit similar to what I mentioned in the previous slides for the change handler implementation. But here, you just define some input, output, and some rules. And here, in this example, a just set from match is a function. So with DD-log, you can implement complex logic in external functions. But you need to implement in a pure functional way. So here are some references. Thanks.
Let's thank our speaker. We have some time for questions, so step up to a mic. Everyone looks a little tired this afternoon.
Yeah, I know.
Oh, here's one.
Okay. I think I know the answer to this, but is there any chance that we'll actually see the C version of OVN controller incremental processing get upstreamed, or is it 100% no, it's going to be DD-log before it's upstreamed?
So basically, I have a branch maintained, I think, since not only we are using, so eBay is already using internally in a live environment. So far, so good. So with decent amount of workload, without incremental processing, I don't think that's possible. But also, there's some people also interested in this. They are communicating with me about the branch. So I'm maintaining that branch until the DD-log approach is finally released. But I'll leave to Ben for the upstreaming part.
So the blame is really on me for not getting that upstreamed, and that's because I'm concerned about maintainability. I find that code, I can't point out ways that it is incorrect, but I also find it difficult to see the correctness, and especially as it changes. And I don't think that you really disagree, but I also understand that you need things to run fast. So
right.
My hope is that we can get the DD-log version to the point where it does everything that we need and does it fast and does it in a way that is easier to see the correctness.
Okay, and as far as the DD-log is concerned, is there some way that those of us sort of looking in and wanting to help out can help out with that?
Yeah, I think basically I want to add to Ben's comment. So the challenge there, the major challenge is 2 points. One is the dependency discovery, make sure dependency graph is correct. I think we're pretty good at that level with the work effort we do. But another thing is correctness of change handler implementation itself. So that for that part, it depends only on the developer's awareness of the logic it's doing, and it's kind of redundant between the change handler and the full compute code. So there's some challenge there. So I think we all agree that DD-log is the approach is the better than the C code to make sure the correctness. So I think I would say let's work on the DD-log first and make sure it can be in reality, and let's try our best together to make that happen. And same time, I think I will still maintain that branch because anyway we are using internally. So welcome if there's interest.
Okay, thank you.
So I think another answer there is that if you're interested in helping out with the DD-log implementation, Justin has been taking the lead over here. You can see him frantically typing away at it at the moment, trying to make sure that it's available as quickly as possible. And Leonard, who's the author of DD-log, is also here. So if you want to find out more about that, you should consider talking to him at one of the breaks.
Okay, thank you.
Let's thank our speaker.